Hello, this is DC Circuits, Lesson 1, and this is the second lecture for Lesson 1. And there's quite a bit to do, so we're going to get on to it. What we're going to cover in this lecture, we're going to review our Week 1 lecture. So we're going to once again look at charges. We're going to look how we develop voltage, how we develop current, what is resistance, what is a complete circuit, and then we're going to go on and we're going to start talking about resistance, different types of resistors, how we read resistors, figure out the values. After that, we're going to go into Ohm's Law and get into the basics of all electronics. So, without any further ado, let's get started. Now, last week we talked about current and voltage and resistance, but before we got to any of those, we talked about the charge. And the charge is just your basic unit of electronics. And whether you are rubbing an eraser on a piece of paper or dragging your feet across the carpet, you're picking up a charge, a static charge of some sort. Whether it's a positive charge, that being an atom that is heavy on protons versus so you've scrubbed off electrons, or whether it's a negative charge and you've picked up a bunch of electrons as opposed to protons. By the way, those atoms that you've scrubbed off the electron from, they are a modified atom, therefore they are known as an ion. And so if I'm talking about a positive charge, I'm talking about ion charge. If I'm talking about a negative charge, I'm talking about an electron charge. So when we start talking about a charge, let me get my pen working for me here, there we go. Whether it's a negatively charged or excess electron charge or a positively charged an ion charge, they are going to have the same quantity of either electrons or protons. And that is 6.25 times 10 to the 18th, which is a lot. It's a big number. But remember, we're talking electrons, so how many angels will dance on the head of a pin? How many electrons is this really? How much room does it take up? So when you have that many, you have the value of 1 coulomb of charge. Okay, the unit of measure in charges is the coulomb. All right, formula symbol is Q for quantity, and the unit of measure is C. So Q equals some number, we'll call it 1 coulomb of charge. We do not forget to tell us what that quantity is, whether it's coulombs or amps. Coulombs, amps, volts, ohms, or watts. We always make sure that we include the unit of measure on whatever we're telling us a quantity. All right, now the great thing about charges is opposite charges, or a potential difference between charges, is voltage. And that is, when we're talking about potential difference, we can have a charge of -1C, and our other charge is a charge of +4C. Well, +4 and -1, that is a charge of 5C, or a potential difference of 5C. And as we remember from last week, opposite charges attract, like charges repel. And so in a complete circuit, where you have, let me throw in a new page here real quick, where you have a plus and minus charge, and then you're running a third charge between them, the electrons in this third charge are going to be repelled by the negative side of your charge, and we'll just make this a battery. There we go, we got a 2-cell battery there. So the electrons are going to be repelled by the negative side, and they're going to be attracted by the positive side. So this is electron flow. And electron flow is always negative to positive. And the reason is the repulsion of like charges and the attraction of unlike charges. And so there we go. And the flow is also known as current. But we'll get back to this because we still have to talk about this potential difference. Okay. Once again, from last week, we talked a little bit about the metric unit of work energy. That is the energy expended to do work. And that is measured in joules. So little w, work, is measured in joules. 1 joule is equal to 0.7376 foot-pounds of energy. So if you expend that much energy doing a certain amount of work, you have expended 1 joule of energy. Of course, once again, symbol for work energy is little w, and it's measured in joules, just like we see here. Now, the reason that is important is when you have a potential difference between 2 points that has the capability of expending 1 joule of energy. Remember, this is a potential difference. It has the potential to do work. When it has the potential to expend 1 joule of energy, moving 1 coulomb of charge between 2 given points, then you have 1 volt. Or 1 volt equals voltage equals work over charge, and that's a little w. Or 1 volt equals 1 joule over 1 C. So that's where we get voltage. That is our basic measurement of voltage. 1 volt is 1 joule of energy moving 1 coulomb of charge. When you are moving that 1 coulomb of charge, you have current flow. The symbol for current flow is I, and its unit of measure is the amp or ampere, and that symbol is capital A. And that is defined, current flow, or 1 amp, is defined as the amount of charge flowing past a given point. So you're actually measuring the actual movement, the actual flow of electrons past a given point in 1 second. Or current equals charge over time, and that time is in seconds. Or current equals 1 C per second. And therefore, the charge can also be defined as current times time. How long has it been flowing? Now, something to remember is current flow is instantaneous, except for in long line applications, just like I put in this slide here. Excuse me. Once again, let's think about a tube. And that tube is full of ping pong balls with a little teeny tiny space in between them. As soon as I apply a force to this end, which represents our potential difference, as soon as I apply a force to that end, this force is immediately transferred to the next ping pong ball, which is immediately transferred to the next ping pong ball, etc., all the way down the tube. So as soon as I start shoving here, that ping pong ball is going to move. Therefore, to our observation, current flow is going to be instantaneous. Now, given that there is a tiny space in between, given applications such as power transmission, where the current is flowing over hundreds of miles of cable, that's going to take a maybe a millisecond or so. Therefore, it's not instantaneous observation through observation in long line applications, because it's going to take a microsecond or so to make it through. So if you could watch the guy in Las Vegas throw the switch at the dam, San Diego might take half a second to get its light. All right, moving along. So now we've got voltage, we've got current. Now we have to have one more piece, and that is the resistor. So resistance is the opposition to current flow. Once again, for formula, symbol is R. The unit symbol is omega, stands for ohms. So we would say resistance equals 1 ohm. Now, of course, conductors, if they had high resistance, they wouldn't conduct very well, so it makes sense. Conductors have a very low resistance. Insulators, something you want to insulate, you don't want to have any current flow. You can imagine it has very high resistance. And of course, the item we manufacture for a specific value, that's called a resistor. Makes perfect sense. Now, 1 ohm of resistance is equal to so many calories of energy burned per second. That exact value, it's in the book. I know it's in the book. I read it just the other day. But it's not something that I personally, as a technician for the last 40 years, have ever really paid attention to. So if you're uber curious about it, go ahead and look in your book and you'll be able to relate calories to resistance. But this will be the last time I talk about calories and resistance. So I'm just moving along. All right, a closed circuit. You don't have a closed circuit unless you have three things going on. You have to have potential difference. Voltage is required, because without voltage you don't have the force to push the electrons, so you don't have any current flow without voltage. There has to be a complete path. Can't have any broken wires, open components. The path has to be closed and complete. And of course, the current path has to have some form of resistance, because resistance is there to either generate heat, such as a heater, or to limit the amount of current that's flowing in the circuit. Because if you don't limit the amount of current, as we know, these are particles. Don't forget, electrons are particles. And when particles move, there is friction. When you have enough friction, you have heat. When you have too much heat, things burn up. So resistance will slow the current. You don't generate as much heat, things don't burn up. It's pretty much as simple as that. All right, problems with any circuit? Well, when you don't have a complete path for your current flow, that circuit is open. The resistance is infinitely high, because unless you're really discharging a lot of current, it's real hard to make air conduct. So if air is not conducting, you've got an infinite resistance, there is no current flow. When the current path is closed, but there's little to no resistance, you've got some path around the resistance, or your resistance is shorted out, so it's no longer a resistor, it's just a piece of wire. Well, we call that a short circuit. And what results from a short circuit? Well, too much current. Too much current, you have too much heat, something burns up, and when we're troubleshooting and something burns up, we generally might say something cute like, we've let the magic smoke out. And that's it. Okay, and for some reason I've got two of these slides in here, so I'm going to keep moving. Here's the drawing of a closed circuit. Of course, this is a battery here, and that would be the plus side. The long side is the plus side. Short side is the minus side. It is your typical closed circuit. You have a complete path, you have resistance, and you have your potential difference. And of course, current's going to flow like that. Or in this case, current's going to flow like that. Remove any of these pieces and you have no current flow, you have no closed circuit. How does current flow? Well, earlier we talked about electron flow, where electrons move from negative to positive due to repulsion and attraction. However, in the real world, most schematics, in the United States anyway, are written in terms of conventional current, where we consider the motion of the positive ions or the positive charges. So you'll often see a circuit drawn something like that, where there's your plus and it's flowing to ground. And even the way we speak in the technical world, something is shorted to ground, we're talking about conventional current flow. Now, it doesn't matter how the drawing is drawn, whether the negative terminal is here or the negative terminal is down here. Electron flow goes from negative to positive, or negative to positive. Conventional flow, positive to negative. Once again, doesn't matter how it's drawn, positive to negative. And that's conventional flow. This circuit is all about DC circuits. DC current flows in one direction and one direction only, from negative to positive. Whereas alternating current, that you find in your house, periodically reverses direction. How frequently is done that? We call one cycle, or the frequency, and frequency is measured in hertz. And taking a picture, hooking up an oscilloscope to a DC line, we go to a flat level, and that's what will be displayed on the screen, just a flat level. If we look at an AC line, we're going to see a sine wave. Now in our household, this sine wave occurs 60 times per second. That is the frequency. That's why we say our houses run on 60 hertz, because one cycle, or 60 cycles every second. And that is pretty much just because when they were building the first AC network, the guys could crank the generator at 60 cycles per second. A little quick bit of trivia on aircraft: we often run 400 cycles per second, and that is, it allows us to reduce the size of the components used in the power system and therefore smaller pieces on aircraft. If the guys way back then could have made their hand crank generator run 400 cycles, we would have a much smaller power grid as far as components go, and we would have a lot less line loss, because we lose an awful lot of power just transmitting from the power station to your home. Another bit of trivia is basically very little stuff in your house actually runs off AC. We plug AC power into it. First thing we do with that AC power is convert it to DC. So really, most of our components in this world, or most of our electronics in this world, runs off DC. We just have to convert it. Thanks to the war between Edison and Tesla. All right, let's move along from here. All right, where do we get sources of electricity? Well, we know all materials have electrons and protons. So it's just what kind of work do we do to separate them to create a potential difference? Because we know potential difference, without it, we can't create current flow. So, common sources, of course. As kids, we had a great time with static electricity, rubbing your feet across the carpet and then touching your little brother or sister. Unfortunately, I was the little brother or sister. Conversion of chemical energy, your wet cells, your batteries. Electromagnetism, motors and generators. Your alternator in your car, great source of electromagnet produced electricity. And photoelectricity, using photoelectric cells or photovoltaic cells, we use light to create energy for electricity. Okay, now we're going to get into the component known as resistors. But first, I'm going to stop talking for just a second, put this thing on pause, and get a big drink from my throat. Okay, that was quick. So now, resistors. Well, we know that we need resistors to limit current, and resistors have got two main characteristics. And the first one is the resistance of the resistor. Of course, once again, symbol is R, measured in ohms. The second characteristic is its power rating. Okay? Power rating, symbol is P, and it's measured in watts. That would be a big W for the unit of measure. And what the power rating tells us is how much power it can dissipate or how much heat it can dissipate. And we'll get to how to calculate that in just a little while. So the resistance R is, of course, the reduction in current, the desired drop in voltage, and the wattage rating, which I just discussed. There you go. Now, the wattage rating is always more important than the amount of power dissipated by the resistor. And what we do is we do our calculations for resistance, current, voltage, and then we do a calculation for the power required for that circuit. And then we double it, and that's the size resistor we put in. So, in this case, here we have 4 resistors, all the same value. They happen to be carbon comp resistors or carbon composition resistors, and they are all the same resistance rating. 1,000 ohms or 1 kilo ohm. But you see, each one of them has got a different power rating. The small one here, he's an 1/8 watt resistor. The next one up is a quarter watt, then a 1/2 watt, then a resistor at 1 full watt. Now for the actual size, up here I have a penny. 1 cent. So you can see the 1 watt resistor is about as big across as a penny. Moving down here, I have a film type resistor. And we'll look at the resistor types in a moment. These guys, we determine their value by the color code of the bands. Okay, this one is brown, black, and red, indicating a 1, 0 with a multiplier of 2, or 10 squared. So 1, 0 times 10 squared, that's 10 times 100, or 1,000 ohms. This one down here is a film type resistor. He doesn't have any color bars on him. He's actually, on the side, is written 1821, which means pretty much the same thing. I've got the first digit, the second digit, then a multiplier digit, plus a digit that tells me the tolerance of that. In this case, it's a 1% tolerance. So 1/8 with 2 zeros, or 1800 ohms, or 1.8 k ohms, plus or minus 1%. Down here is a wire wound resistor. He's real small. He's actually 10 ohms, but he will dissipate 50 watts of power. 50 watts produces quite a bit of heat. So this is wire wrapped around a ceramic core, then covered in a high temperature epoxy. And you find this, once again, in high power applications. So we just looked at some of these resistor types. There's the wire wound, which are generally high power and high wattage. They're also quite handy. They're used in rheostats. which is a type of adjustable resistor. Carbon composition resistors, well, mostly made out of carbon. Higher or lower tolerance, that is to say, if I have a 20 ohm resistor, it can be have as much as a 10% tolerance. So it can be 18 or 22 ohms. So that's pretty wide tolerance. Film type resistors, also carbon comp, tend to age faster than most of the resistors. Once again, you're pumping current through them, you're heating them up, you're cooling them down. The electrons themselves are abrasive. So these carbon comp types resistors will break down over time. Film type resistors, well, you do have carbon film and metal film. The construction is essentially the same, it's just the material's different. And these guys, once again, can be down as low as 1% tolerance. ENCE, ANCE. Another type is a chip resistor. These are very small. Your cell phone is full of them. Your computer is full of them. They mount directly to a circuit board. There's no axial leads, and it's no wires. And we'll take a look at some more of those in a minute. Fusible resistors, resistors that are fixed value, but they are made to open up if their power limit is exceeded. So they work as both a resistor and a fuse. And then thermistors. A thermistor is a resistor that changes its value as it either heats up or cools down. Some of them have got a negative coefficient, that is to say, as the temperature goes up, the resistance gets lower. Others have a positive coefficient, meaning as it gets hotter, it gets to have more resistance. Pretty straightforward. Okay, wire wound resistors. Once again, this guy is your rheostat, which is a variable resistor. Let's see here. Actually, this one is a potentiometer. A rheostat has got two leads, one of them being the adjustable one, and you can see how it rubs on the wire, so as you change it, it's going to give you a different resistance. Because it has a third leg on it, it is a potentiometer. And we'll go once again into the difference in just a moment. So once again, wire wounds used for high current, low resistance, and lots of power. This is the ceramic variety. This is the adjustable rheostat or potentiometer. Carbon comp, so they made a mix of carbon and graphite with an insulating material. You got metal caps on the end for the axial leads. That's what these guys are called, axial leads. And that's how you solder it to the circuit. They say it's becoming obsolete because of the carbon film resistors. However, because these guys are still so cheap, you're going to find them in everything. Computer power supplies, all kinds of different things still use these. So they keep saying they're becoming obsolete, but I'm still finding them. Film resistors, and the film is a type of resistor. This one just happens to be carbon film. Alright, once again, they've got layers of ceramic in between layers of carbon with an epoxy coating on them. They age much better. They're less susceptible to changes in temperature. They produce less noise. They're a good item to use, but they're a bit more expensive than normal carbon composition resistors. Metal film resistors, same thing. Basically same construction, same advantages. Disadvantages, they're still a little bit more expensive, and manufacturers are still using the cheaper stuff. Here's your surface mount. You can see by the magnification on the pencil tip, they're very small. they're identified by, once again, writing right on them. In this case, it's a 391, so 390 ohm resistor. 39 and 10. They might also be color coded with dots as opposed to the writing, which in this case it would be orange, white, and brown. 3 dots, orange, white, and brown. All right, fusible resistors we talked about. Thermistors we talked about. Okay. Carbon resistors, because of the size, especially in the 8th watt variety, it's hard to mark them with writing. So we use a color code system. And the colors, each one represents a numerical value 0 through 9, and the coding is standardized. And the coding looks like this. Black is 0, brown is 1, red is 2, etc. all the way through. So the bands on a resistor, we look and we say this is your first digit, here is your second digit, just like the graphic says. Then your multiplier, and that is decimal multiplier, so we're talking times 10 to some exponent. So if it's a red band like this one is, then it's 10 squared, or 2 zeros after the first and second digit. The third or the fourth band is your tolerance band. Now with carbon resistors, you're going to find gold or silver, where gold is 5%, silver is 10%. And that means if it's a 100 ohm resistor and you got a 5% tolerance, then you can be 105 to 95 ohms. Okay, 5% of 100. Somewhere in that range. We don't normally give an entire range like this. What we would say is this guy is 2.5 k ohms plus or minus 5%. That's how we would express the value for this resistor. Now there is a mnemonic for remembering this, and this is a more politically correct, gender-friendly mnemonic than the one I learned way back when in technical school. So starting with the color black or the value of 0, bad boys race our young girls, but violet generally wins. And that will give you your values 1 through 9. And it'll help you remember your values. And here we are. Let's see, when did I go through technical school? 1979. So however long ago that is, that's how long I'm remembering this. Okay, so here's some examples. We just did this one. Here we have red, green, black with a gold stripe. So this is 250. That black means there's 0 zeros. So this is just 25 ohms plus or minus 5%. Coming over to this one now, if we are going less than 10 ohms, then we have to have a way of saying so. I should say, yeah, less than 10 ohms. And here's where we have, pardon me, moving the gold stripe up into the third position makes it a modifier. So in this case, I have 2.5. Okay, red and green, 2.5. The gold says that is times 10 to the minus 1, or times 0.1, which would make it 2.5, and with the silver tolerance band, plus or minus 10%. So in the third position, if you get gold, it's 0.1. If you get silver, you multiply by 0.01. So you can end up with a value of less than 1. And there are times where you're using very small resistor like that. Let's see here. All right, we already talked about tolerance. So in this case, here we have a yellow, violet, so 472, so 4700. There we go, right there, 4700 ohm. With a gold stripe, 5%. If we take that 5% into account, we can go 235 ohms either way of 4700. So 4465 or 4935. So you see, a resistor can have quite a large swing, depending on its composition. In this case, it's a carbon comp. A big problem I have for some of these is that looks like green, violet, and brown to me. So you have to also pay very, very close attention to your color codes. And this is just because I'm a little bit partially colorblind from just too many cracks to the skull over the years. All right, and here's another set of color code ranges. By the way, most of this that I'm presenting here can be found in your Lesson 2 PowerPoint slide, or your Lesson 1 Chapter 2 PowerPoint slides. So download them, go ahead and review them. And you can see 1K ohms with a 20% band. You notice you don't start at the gold or silver band when you're looking at the value. You start at the plain paint band. So 20% of 1K is 50 ohms. So you can go above and below by 50. Did I say 20%? 5%. 5%, not 20. And all of these are 5%. So quite a swing on the different values. Now, precision resistors, you're going to find a little bit bigger color code. In this case, it's a 5-band. So you have your first digit, second digit, and a third digit. With your multiplier, and then your tolerance band. And in a 5-band code, there are your tolerances. So you see, we're going pretty tight tolerance. Brown being 1%, green being 0.5%. We can get all the way down to 0.1% for a tolerance. So with the metal film resistors, you can get quite the tight tolerance. And of course, you'll be going for for your tolerance band, it's the one farthest away from the edge. Your first numeric band will be closest to the edge. And then 0 ohm resistor, it's basically a fuse. We're using it as a jumper. If our power is exceeded from its power rating, either an 1/8 watt or a 1/4 watt, it will open up and become a fuse. Variable resistors. Now you've seen the symbol, that being your normal standard fixed resistor. Well, a variable resistor will have an arrow through it, indicating you can change, indicating you can change the position, which will change the resistance between this terminal and one of these two terminals. So a rheostat has got two terminals. So the resistance from here to here is going to change depending on where you adjust the adjustment to. And this is same thing, just upside down. That's a rheostat. There's two terminals. They're usually connected in series with the load and the voltage, and what their primary function is to vary the amount of current that's being used in the circuit, because if you change the resistance, you're going to change the amount of current. Potentiometers have got three terminals, and they're usually leading off to some other circuit somewhere, and they're used to vary the voltage going out to that other portion of the circuit. Okay, once again, rheostat, big old wire wound device here. You got a fixed contact and the variable contact. And once again, when you put it into the circuit, they're putting it in series with a fixed resistance, and it is going to vary your current. And it doesn't matter which way we're doing it here, it's going to do the same thing. Whereas potentiometer, we're starting with 100 volts there, but depending on where we adjust that center tap to, we can either have 0 volts or 100 volts or anything in between. Measuring with a voltage meter out there. Now, the schematic for it would look kind of like that. All right, as I said, power rating. Not only do you have to consider resistance, but you have to consider the amount of power in the circuit. And we will look into the calculation in a moment. So the larger size of the resistor is going to be an indication of its power rating. The bigger the resistor, the more power it'll handle. And a higher power rating means you can handle more heat, greater temperatures. But the problem with that is big, so they're also changing the space. They're limiting the amount of space you have. So choosing the right size can be important. Okay, what kind of troubles do resistors cause you? Well, as we said with the carbon comp, over time they can drift out of tolerance. When they drift far enough out of tolerance, if they go too low, you're going to have too much current. Your resistor is probably going to burn up. If they drift too high, they're going to reduce the amount of current you have in the circuit, and it's just not going to function properly. Controls, rheostats and potentiometers can become dirty or noisy. So as you, like in your car radio, turning it up or down, you can get scratchy sounds. I don't know if too many radios actually have that kind of knob anymore. But when they are in the old-fashioned stuff like I have, you can hear the noise coming through the speakers. Or resistors can just short out internally. They may become a piece of wire and form a short circuit, too much current, something else burns up besides them. You can usually find the ones that do because they've pretty well blackened the inside of the structure that they're in. Okay, open resistor, of course. We usually don't do a schematic of an open resistor, but that's an open resistor. You don't have a complete path for current to flow. Out of tolerance, well, you got a 1K resistor with a plus or minus 5%, and when you measure it, it's 1.5K. That's out of tolerance. So you've got too much resistance there. We measure resistors with an ohm meter. So an ohm meter has its own voltage, so you got to cut off voltage and generally isolate the circuit you're measuring from anything else. And as an example of that, let's see here. I have to get to the right device here. And let me bring up my camera. Okay, I'm actually measuring this resistor here, and it's saying it's 2.98 kiloohms. if we look, we see my tolerance down here. Well, let's make that a little bit bigger. My tolerance down here is on the 20 k ohm scale. So that is 2.98 k ohms. However, that's not the accurate measurement. And the reason it's not the accurate measurement is because right there I have a voltage regulator in the circuit. So this meter is currently not only looking at the resistor, it's also looking at that voltage regulator. Now, I'm able to isolate the circuit simply by pulling off the power lead, because that's what's bringing the voltage regulator into the circuit. So now I'm measuring pretty much what I ought to be, 4.16 k ohms. This is actually a 3.9 kilo ohm resistor, plus or minus 10%, I think. So that's what happens if you don't isolate it from the rest of the circuit. And let me get rid of this and take them down. So, like I said, an ohm meter has its own voltage source, so voltage must be off in the circuit being tested, otherwise the ohm meter may become damaged. And let me bring that back out and go that way. Okay, this is what it looks like when a resistor goes out of tolerance or gets too much current. That is a nice charred resistor, probably had a bit of smoke and a bit of stink going for it too. And that's pretty much it for resistors. Now we get into the fun part. And the fun part is Ohm's Law. Now, Ohm's Law states, in its pure form, that in a circuit, the voltage is equal to the current times the resistance. Or in our graphic form over here that you should never forget, because this is what we call the magic circle, voltage is equal to current times resistance. Now, since that is true, we can derive a couple more equations. The first one being current. Well, current is equal to voltage over resistance. Or for resistance, resistance is equal to voltage over current. And we remember that I is current, V is voltage, and R is resistance. This is the basis of all of our DC circuits right here. Now there's one other equation that we'll look at, but this is the basis for everything else. Whoops. Well, let's go ahead and get rid of that one too. There we go. So in this little drawing here, our light bulb is a fixed resistance. Now that's not actually true in light bulbs, but in this case it is. This is a fixed resistance of R. In this case, as we vary the voltage, right now we're sitting at 12 volts, but as we bring it down through all the steps down to 2 volts, we will see this light bulb getting dimmer and dimmer and dimmer. That's because V equals IR, say the resistance equals 1. That makes voltage equal current. So as the voltage goes down, the current goes down. If the less current means less heat or less glowing tungsten filament. This also shows that voltage and current are directly proportional. for a fixed resistance. All right. So, looking at our three forms of Ohm's law, you can see 1 amp equals 1 volt over 1 ohm. Or 1 volt equals 1 amp over 1 times 1 ohm. Or 1 ohm equals 1 volt over 1 amp. Don't know why this was important, but I just re-explained it to you. Now, applying Ohm's law. It's quite simple. Once again, I have two knowns. I have 20 volts and 4 ohms. So I'm going to apply the current form of Ohm's law. So current, I, is equal to 20 volts over 4 ohms, which will equal 5 amps. So in this case, current equals 5 amps. Remember, I for the formula form, A for the unit of measurement form. Okay, in this case, my two knowns are current and resistance. So I know current and resistance, will apply the voltage form. Voltage equals 1 amp times 12 ohms, or voltage equals 12 volts. Finally, we have a known current, we have a known voltage. We go to the resistance form. 6 volts over 3 amps is equal to 2 ohms, or resistance equals 2 ohms. It doesn't matter what kind of circuit it is, Ohm's law applies. So whether your unknown is voltage, or your unknown is current, or your unknown is resistance, using Ohm's law, you can determine the unknown. Now, the units of voltage. I keep going back to using metric forms. So when you're talking thousands of volts, you're talking 10 to the third, or the kilovolt. If you're up in the megavolt range, you're talking megavolts. If you're less than 1, in the 1/1000th range, 10 to the minus 3, you're in the millivolt range. So we want to use millivolts. 1/1,000,000th, the microvolt range. So we're going to say 10 kilovolts, or 10 microvolts. Same thing goes for current. We're usually working in the milli or microamp range, though we can get up into the amps range. If you're getting up into the mega amp range, you're working nuclear power, and that's not DC circuits. Okay, resistance, kilo ohm, mega ohm. Very rarely are we working in the milliohm range. So it's usually mega ohm and kilo ohm, or just plain ohm. Alright, going back to the proportionality. Here's a graphic that is stating exactly what I said. Here's your circuit. In this circuit, I've got a current meter installed, so I can read what the current is. And at all times, we're talking 2 ohms of resistance. Now, as we vary the voltage from 0 to 12 volts, we can see that we have a direct linear slope to our current to volts. So it's a direct linear slope, as shown here, because current and voltage are directly proportional for any one value of resistance. At the same time, for a value of voltage, for where voltage is constant, current and resistance are inversely proportional. As current decreases, resistance has to be increasing. More resistance means less current. If current increases, resistance has to be decreasing, because you're reducing the resistance to the flow of current. And so, since they are directly proportional, if resistance doubles, current will be cut in half. If resistance is cut down to a quarter, current will increase by 4 times. Current and voltage have an inverse relationship. Now, up to this time, I've kept it to voltage, current, and resistance. There's one other aspect that we have to consider that is part of Chapter 1. It's also part of Chapter 2. Right now we're working, as you see, in Chapter 3. And that part is conductance. And you've already had a question about conductance. Conductance, its formula symbol is G. Its unit of measurement is the Siemens. Or Siemens, I think it's, or S, there we go. And conductance has a relationship to resistance. And that is conductance equals the inverse of resistance, which also means resistance equals the inverse of conductance, which should make sense. If a wire, as in your question from this weekend, I'll throw in a new page. This past weekend you had a question where it was a conductance of a wire at 100 degrees C equaled 1/10 the conductance of the wire at 25 degrees C. It should have been G. And at 25 degrees C, the resistance equaled 10 ohms. Now there's a couple things to calculating this out. Number one, you have to either work in resistance or conductance. You can't work in both at the same time. But here we have a known resistance, and we're given a scalar for that resistance. So the conductance for this piece of wire is going to equal 1 over its resistance, or at 25 degrees C, it's going to equal 1 over 10 Siemens, or 0.1 Siemens. So we can then just stuff that in here. So the conductance of the wire at 100 degrees equals 1/10 0.1 Siemens, or equals 0.01 Siemens. Now we need to know what the resistance is at 100 degrees. Well, R equals 1 over G, so which equals 1 over 0.01, which equals 100 ohms. So you see, as the conductance gets lower, okay, lower number on the conductance, 1/10 or 0.1 at 25, 0.01 at 100. So as conductance got smaller, resistance got higher because it wasn't conducting as well. It had more resistance. So resistance equals 1 over conductance, or conductance equals 1 over resistance. We know that current is also inversely proportional to resistance. Therefore, conductance and current are directly proportional. This is going to come in handy later. The proportionality between conductance and current will come in handy when we get into parallel circuits, which is next lesson, which is in 4 or 5 weeks from now. Alright, so a linear resistance is a resistance that doesn't change. So if you have a linear resistance going on, fixed value, voltage and current are directly proportional. So film type resistors, things that don't change due to temperature or whatever, as long as they stay constant, current and voltage are directly proportional. And here's a case. You take this resistor, change it to 1 ohm, all you're doing is changing the slope of the curve between volts and current. Same thing here, you've changed it to 4 ohms, you've changed the slope of the curve, but you've not changed the linear proportionality between voltage and current. If you put in something that does change with temperature, of course, you won't get a straight curve because the resistance is changing at the same time that the voltage and current is changing. Okay, in this case, the resistance is getting greater, so the change in current is sloping off. In this case, this is a negative temperature coefficient thermistor. As it gets hot, its resistance decreases. Therefore, you see the slope of the current curve getting steeper because the resistance is going down and therefore the current is going up. So this is a nonlinear device. Now let's put all this to the test that we've looked at so far in just the basic form of V equals IR. And we're going to go back to my camera. Whoops. And let me throw another new page up here. In this case, I have got a 5-volt voltage source. I have a current meter. I have my resistor. And I also have a voltmeter. Now I will set my meters up. And let's ignore the fact that we can see the color code on the resistor right now. And let's just apply our power. Now here's a 9-volt battery feeding a voltage regulator that's way over here. And that voltage regulator is feeding my power bus. My power bus is the red and the black terminals there. Now this red terminal is going to my current meter. going through my current meter, and then the yellow wire here is the first attachment to my resistor. So that's going to be, see, that's a red, that's a yellow, that's a red, that's a black, and from here to here is just the leads to the resistor. And then the resistor goes into the ground bus, which is directly connected to the black terminal here. So I can see on my voltmeter, I have, let's see here, let's stabilize again. Make sure I've got everybody plugged into where they ought to be. And everybody nice and stable there. All right. I'm going to call that 5.01 volts. And now my current I see is 1.2 milliamps. Right there is my current scale, and that is maximum of 20 milliamps. So 20 milliamps, 0.020 is max. I'm reading or 1.2 milliamps. So 1.2 milliamps. Alright, so let's see what the resistance is. The actual resistance, not what's marked on the resistor. Well, the actual resistance for this whole circuit, I'll bring my calculator down where we can see it, is 5.01 volts divided by 0.0012, that's 1.2 milliamps, equals 4.175 kiloohms. So let's see how close we actually are to that as far as our meter measurements go. And I'm going to give my meters, say, a 10 to 20% tolerance because they are fairly cheap. So coming back to here, I'm going to remove power because, of course, an ohm meter has its own source. I'm going to take this down to 20k ohms maximum, and I'm going to isolate from the circuit. So 4.16 kiloohms is what I'm measuring, and my calculator said it should be 4.175. I'll take 10 to 15 ohms out of spec on that. So that pretty well proves Ohm's Law does work. Now, what is a little disturbing is if I come down closely here, so we can read the color bands, we've got 392 with a gold band. So that should only be 5%. So let's come back up here and say 3900, 39 with two zeros, times 0.05 equals 1.95 plus 3900 equals, see, so my resistance there is a little bit high from what it should be according to the markings on it. But the actual numbers read by the meters work out. So you can't always trust the color code. It's going to be close, but it's not necessarily going to be perfect. Okay, get rid of that. That's out of our way now. Now our schematic's out of our way. All right. So far we've taken a look at voltage, current, resistance. We've had a look at Ohm's Law. Now we have to talk about electric power. Of course, the basic unit of electric power, capital P, is the watt, capital W. And of course, we have our units, so kilowatts, megawatts, milliwatts, microwatts. Just depends on the device what it's going to draw. And how do we calculate power? Well, power in a given circuit is equal to current times voltage. That is our basic power equation. And we actually have a magic circle for power too. Okay, and power is the time rate of doing work. So we can also relate power back to work energy. And what's work energy? The joule. So power not only is voltage times current, power is also equal to work over time, which means work is equal to power output for the amount of time that the power is being done. So power is the time rate of doing work. So work per minute, work per hour, work per second. Where work is power for how long you're doing it. Now, we've already said power equals voltage times current. We also realize that, voltage is equal to work energy over charge, whereas current is equal to charge over time. So power being voltage times current, it is then also equal to 1 joule per coulomb times 1 coulomb per second. Well, the charge cancels out, and you end up with work over time. Power equaling work over time. And so, when we're talking about the circuit that we just had here, my little circuit, let me get that back, let me fire it back up. This, believe it or not, is our most useful form, but this comes in handy too from time to time, because from time to time we will be asked about expenditure of joules and how does that relate to everything else. Let's see here. I'm still looking at 5 volts and 1.2 milliamps. So the power consumption of my little circuit equals the voltage times the current, and let's not forget the unit of measure, which is going to equal, let's bring the calculator back up again, 5 volts times 1.2 milliamps equals 0.006 or 6 milliwatts. So my power consumption here is 6 milliwatts. Now that 6 milliwatts is 6 milliwatts every second. Okay, so coming down to this, equation down bottom here. So 6 milliwatts equals some work energy over 1 second. Because when we do this measurement, this is what happens in 1 second of time. My measurement for current is that much current flow in 1 second. So 6 milliwatts every second the thing runs. So 6 milliwatts equals 1 joule per second, or 6 milliwatt seconds equals joules. So I basically have 6 joules. Well, pardon me, 6 millijoules. So power is then going to equal 6 millijoules of work being done by my little single resistor circuit. Kilowatt hours. When we're paying for power, we're paying in kilowatt hours. Now, that means we're paying for 1,000 watts or some portion of 1,000 watts per hour. Now, if my little circuit here, which is 6 milliwatts, that is actually 0.0000006 kilowatts. 0.123123. Yep. That is 0.000006 kilowatts. If I use that for 1 hour, if I run this circuit for 1 hour, I've used 0.000006 kilowatt hours of electricity. That's what I will be billed for. So is the actual amount of work energy times the time in hours that's being used. And it has to be expressed in kilowatts. So if I've got something that is using, it's rated for 100 watts. If I've got a device rated for 100 watts, that is 0.1 kilowatts. If I use that for 2 hours, well, then I have to actually multiply it. That would be 0.2 kilowatt hours. 0.1 times 2 is 0.2. And that's what I'm paying for. Once again, something rated at 10 kilowatts for 1 hour, that is 10 kilowatt hours. If I'm using it for 4 hours, that's 40 kilowatt hours of power that I'm paying for. Let's see here. I think my household goes through 1,300 kilowatt hours a month. So that's quite a bit of power being used. All right, and so here's a good example. We've got an item that runs off 240 volts and it uses 20 amps. So 240 times 20, that's 4,800 watts. Converting to kilowatts, that's 4.8 kilowatts. If it's running half the day, that's 4.8 kilowatts times 12 hours, or 57.6 kilowatts, at a rate of 8 cents per kilowatt hour. I wish, because I'm paying 15. So 8 cents per kilowatt hour, that's 57.6 kilowatt hours times 8 cents, or $4.61 a day we're paying for that air conditioner. And wouldn't that be nice if that was true? Okay, and that is where I'm going to call it for today. So, today we looked at a quick review of Chapter 1, where we got voltage, where we got current, where we got resistance. We looked at Chapter 2, different types of resistors, the power rating of resistors, fixed resistors versus variable resistors. And we've looked at Ohm's Law and power equations. Next time, we're going to continue with the power equations, and we're going to go through all the different variations on Ohm's Law and power, and how the two will interact with one another to allow us to do all kinds of calculations with very little data. So, like I said, that'll be next week, and if you have any questions, of course, you can always get hold of me. You know the different ways to do it. Read your book. Don't forget that you still need to do exercises, even though they're not due till the middle of February. It's good to get them done ahead of time. That way I've got a chance to look them over, tell you what you've done wrong or what you've done right, let you take another shot at them. Once again, we're here to succeed. We're not here to watch you fail. So you guys be good, and I will catch you next time. Bye.